Have you ever tried to put order into your room, or maybe on your desk, or in your children's rooms, or have you ever been told by someone else that you needed to organize that room once and for all? If you have any experience in this, you know that this is a task that may be unpleasant but needs to be done. Now, why does it need to be done? Why do we need to put things in order? And since we're at it, what does it even mean to put them in order? Sometimes the reason why many people have a hard time getting things in order and organizing their desks and so on is that they're not quite clear why you would need to do it, and also what is it that you're trying to accomplish. So in this class, we're going to actually look at this very issue of getting things organized together with what does it mean and why are we doing it. Of course, we're going to do it in the context of linear algebra, so from the one point of view it's going to be more abstract, from the other point of view it's going to be a little bit simpler because we're only going to be dealing with certain very specific objects. So let's see what we're talking about. Now you remember that given any basis for a subspace S of Rn, so consisting of vectors u1, u2, uk, any vector in that same subspace is a linear combination of those vectors ui. In fact, I can say that for any subspace of any vector space, not just of Rn, but in fact for what we're going to be doing in this class, we're going to stick just to Rn, so that's why I'm saying it this way. So what does it mean? That means that given the vector x, I can write x as, well, the vector u1 times some coefficient a1 plus the vector a2 times some coefficient a2, etc., etc. And not only we've seen that, but we've also seen that these coefficients are unique, and we call them the coordinates. They are unique in the sense that there is only one choice for a1, for a2, and for ak, so that x is going to be a linear combination of those k vectors. Now the question is, how can we find the coefficients? So if we're given a basis and if we're given a vector x in the same subspace which is spanned by that basis, how are we going to find the coefficients that we need? Well, now if we are in Rn, and this is what we're going to be playing in Rn, then in general we can find those coefficients by solving a linear system. In fact, if you think about it, what you have in front of you is exactly a linear system in a1, a2, ak. Those are going to be our variable. Those are the numbers we need to find. Now we know how to do that, but we also know that that involves setting up a matrix, doing the RREF, and then finding the solutions, etc., etc. So what we're going to be looking at is, can we organize our basis so that finding those coefficients is going to be easier? It turns out that in fact there is an easier way, as long as we're dealing with a special basis. So what we're going to do is organize our basis, change from our basis to a different one, and first of all find out what different one we need, so what kind of order we need to put, so that this task of finding the coefficients is going to be easier. So first of all, let's see what order means in this context. So what are we trying to achieve? What kind of bases are good for this purpose? So in order to move further towards this idea of what bases do we need and how do we find them, let me give you a little bit of terminology. This is linear algebra after all, so we do need new names every time. So first of all, we're going to say that a set of vectors is orthogonal if any two of them are orthogonal. So not really anything new, except the old concept of orthogonality, which is the same thing as being perpendicular or dot product equal to 0, applied to a whole set. So if I have not just two vectors but several vectors, I'm going to say that the whole set is orthogonal if whenever I pick any two of those vectors, they are going to be orthogonal. An orthogonal basis, therefore, is a basis that forms an orthogonal set. Similarly, an orthogonal set of vectors is said to be orthonormal. These words are becoming messier and messier, aren't they? So it's going to be orthonormal if all its vectors are unit vectors. So not only they are orthogonal to each other, but each one of them has length 1. And so correspondingly, an orthonormal basis is a basis that forms an orthonormal set. So this is the kind of things that we will be looking for. Why? Because these are nice sets and nice bases. Let me explain what I mean by saying that these are nice sets and bases.